Okay, students, so regarding the topic Lienard and Wiechart potentials, last time what we did that we were talking about retarded potentials. So what were retarded potential? That suppose if source is present at some point r dash and observer is at point r and there is some significant distance between them, so that the time taken by the signal to travel from this to this point is actually significant. It means there is a difference between the time at which the signal travels and the time at which signal arrives. So the potential which we are calculating at some position r and t is at the present time, whereas the signal traveled at some retarded time. So all the potentials which we are calculating now are the potentials which traveled or which have the information of the source at a retarded time. So all these potentials are retarded potentials. Okay, so in the retarded potentials, initially we saw that potentials and the fields can be found by the usual method. But let's suppose now the source is traveling. The source is not on its usual point, and now it is traveling at some trajectory, and we will say this: the distance between the source and observer is now r minus wtr, where this w, this position vector of the source, is a function of retarded time. So what will happen at that time? Okay, so we cannot exactly write r by c because now this is also the function of retarded time. Okay, so what will happen in this case? So now wtr is the position at retarded time, and r, the distance between the source and observer, that is r minus wtr. So the retarded potential will be given as rho r dash tr by r. Initially we were having this r, and now we are having this r d tau dash. Okay, so this denominator, it is distance to the retarded position of the charge, that's okay. And numerator is rho r dash tr d tau dash. It is giving you the total charge of the entire distribution calculated over different instants at its trajectory. Mean if it is here, it is changing. So at a particular instant we are finding this rho tr. Now to check the traits of this thing, because now there is a relative motion between the source and the observer, so we will take help of the Doppler effect. So what happened in the Doppler effect, that if you have any 3D object and the object is coming toward the source, okay, so the object is coming toward the source, because it is 3D, it may have length, breadth and height. So the length, breadth and height, so only that dimension will get affected which is traveling toward the observer. So for example, the apparent and actual length will be changed by L dash is equals to L1 minus V by C if it is coming toward the observer, or it is going away from the observer, a plus and negative sign, that we already know. But the other two dimensions, height and width, that remain unaffected. Okay, so it means if a 3D object in having some volume, it is approaching toward the observer, so the change in actual and apparent volume will be given as tau dash is equals to tau 1 minus V by C. And to give it a direction, so the direction is with respect to the observer. So the direction is in this direction. So direction of this change or this relative motion will be toward r cap. So we have put r cap here. So what will happen to this rho tr over the d tau? It will be given as rho r dash tr d tau. It will be what? Rho d tau. For d tau, with d tau dash we have rho d tau over 1 minus r dash dot v by c. And what is rho d tau? Rho d tau is nothing but q, total charge. So the integration of this thing will be equals to a simple q over 1 minus r cap dot v by c. So if you put it in the v, so just check in this integration, this r is having dependency on r position vector, which is independent of primed coordinates, w position vector, which is again independent of the primed coordinate, and this is the integration with respect to the primed coordinate. So you can skip r out from the integration and treat it as constant. Okay, so we have done the same here. So this is the potential, a scalar potential for a source which is in the retarded time, which is changing its trajectory. So there may be possibilities that on this trajectory the source will be given multiple signals, that due to these multiple signals there may be confusion about the actual position of the source. So is it possible or not? So to check this, suppose 2 points from the trajectory are communicating with the observer at r at time t. So what will happen now? This r, the relative distance, this r is r minus wtr, or it is simply, what is this thing? It is the distance traveled by signal from source to observer. That's okay. And the distance can also be given as speed into the time. So t minus tr is the time taken by source signal to travel from source to observer, and c, we have kept speed of light here, c, which is for signal, and this is the distance traveled by signal. Okay, so this is in term of distance and this is in term of speed into light. And now source is also moving. We don't know about the velocity of the source. Of course the velocity of source is not c, right? So this position vector is concerned with the velocity of the observer, velocity of the source, which is not c, but this is concerned with the time taken by signal to travel, which is with the velocity c. So suppose if there are two signals, r1 c t minus t1, r2 c t minus t2, coming at two different instants, so r1 minus r2 will be equals to this thing. So it means r1 minus r2 is the position vector of observer and the source, and this is equals to speed of light multiplied by some time gap, right? So it means it is giving you the false information that the source is traveling with the speed of light, and which is not possible because no charged particle can move with the speed of light. It means r1 minus r2 should be equals to 0, or r1 is equals to r2, or it means there is no multiple signal coming from the trajectory at the same time to the observer. So only one retarded point is contributing to the potential at a given time, right? So going back to here, 1 over 4 pi epsilon naught 1 over r q, this thing we can simplify this by putting r cap is equals to r vector by r. Just put it here. You will do some calculation, and this will be the potential, the scalar potential, right? And to find the vector potential, mu naught over 4 pi, we have it is here j r dash tr d tau. Now we will try to make the things in terms of rho, which we already know, which we have already solved. So j is equals to rho into v. V is the velocity of what? Velocity of the source of the charge distribution, which is not c, which we already talked about just, and it is also the function of retarded time. Of course, if you look at the integrand, it is on d tau dash, it is dependent on retarded time, it is also dependent on unprimed r minus w, which is a function of retarded time. So it means this and this factor is independent of d tau dash. You take it outside. What is rho d tau? That we already know, and you just solve it a little bit, and this is the potential. So if you compare these potentials with the initial potentials, you will just note that we have an extra thing, which is r, and now this r is equals to r minus wtr, and you have two velocities. V is the velocity by which the charged particle or the charge distribution is moving at some trajectory, and c is the signal, the speed of signal, which is coming from the charge distribution to the observation point, right? So this v and a, the vector and scalar potential, in case when the source is moving in retarded time, are given as these two things, and we collectively call them Lienard and Wiechart potentials. Now you can have a relation between a and v. How? If you closely just monitor, this thing and this thing is same, only there is a factor change here. So you can just put it equals to put the value of qc over this factor, and which is equals to 1 over 4 pi v, this thing, and at the last you will just receive a is equals to v by c square, v potential into r and t. So all these are the forms of Lienard and Wiechart potentials.